Welcome to the Explainer. If you're a focused learner looking to truly grasp the mechanics behind your code, you are absolutely in the right place. Today we're taking a structured look at something that trips up so many developers, and that's Docker networking. Our goal here is to completely demystify exactly how containers on your system talk to the outside internet, and just as importantly, how the internet talks back. Okay, let's dive right into this. Here's our roadmap for the Explainer. We'll start with the isolated container world, move to the virtual network cable, look at outbound traffic reaching the internet, inbound traffic reaching the container, and finally, some golden rules for Docker troubleshooting. Section 1. The isolated container world. Establishing the basics. To truly understand Docker networking, we first have to look at the environment itself. Think about your laptop for a second. It has a physical network card that handles all of your internet data, right? But your Docker container runs in total isolation. It doesn't directly use your laptop's network card at all. So how do we bridge that gap? Well, by default, Docker puts the container on what's called a bridge network. This is essentially a software switch that Docker quietly creates inside your host machine. Any container you start automatically plugs right into it, bringing them out of isolation and onto a little private network. Now, because these containers are plugged into the exact same private network, they can reach each other directly using their internal IP addresses. You don't need any port publishing or complex translation for them to chat. However, if you were to spin up multiple bridge networks, which you can absolutely do, containers on different bridges simply cannot talk to each other by default. They're entirely separated unless you explicitly attach a container to both of those networks. Moving on to Section 2, the virtual network cable. Connecting the dots. So we know the container and the host have the software bridge between them, but how exactly are they wired together? To solve this, Docker creates a virtual Ethernet pair. The source material has a brilliant way of framing this. Think of this virtual Ethernet pair like a virtual network cable with two ends. One end goes straight inside the container. This connection point becomes the container's door to the outside, and we usually refer to it as ETH0. The other end of that cable plugs directly into that Docker bridge network we just talked about. Let's move to the exact path and see how this builds. Data starts at the application inside your container. It moves out through the container interface, ETH0, travels right along that virtual network cable, hits the Docker bridge network, and finally reaches your host machine. From the host, it then gets pushed out through your real physical network card to the vast internet. Take just a second to visualize that step-by-step flow because it's the absolute foundation for everything we're about to decode. All right, Section 3. Outbound traffic, reaching the internet. Let's trace our first critical data journey. Imagine your container is running a web server like Nginx, and it needs to reach out to the internet to pull down a software package. To understand how this works, we really need to look at the IP addresses involved. Your host machine sits on your real network with a real IP address. Maybe it's 192.168.1.10. But the Docker bridge network gets its own private internal address acting as the gateway, usually 172.17.0.1. And your container? It gets an IP on that same private subnet, let's say 172.17.0.2. It's absolutely crucial to internalize that this container IP is completely internal to your laptop. Which brings us to a massive, glaring problem. If your container's Nginx app sends a packet out to the internet, its return address is stamped as 172.17.0.2. Pause and think about that for a second. If that packet went out to the public internet exactly as is, how does a public router know where to send the reply? Spoiler alert, it doesn't. No router on the internet knows what your private 172.17.0.2 means. The reply would literally just vanish into the digital void. So the crucial point is how Docker elegantly fixes this using a clever trick called network address translation, or NAT. Under the hood, Docker sets up a rule using IP tables. As the packet leaves your host machine, the host rewrites the source address in the packet. It swaps out that private container IP for its own real IP, the 192.168.1.10. To the rest of the internet, the traffic looks exactly like it came straight from your laptop. The container itself is completely invisible. Then, when the internet replies to your laptop, your host remembers, oh right, this one belongs to the container, rewrites the destination back to the private IP, and sends it safely down the virtual cable to ETH0. Section 4. Inbound traffic, reaching the container. Now, this second journey, reaching into the container from the outside, is where the vast majority of confusion originates for developers. Let's look at a scenario we've literally all experienced. You've got an Nginx server running perfectly inside your container, listening on port 80. You open your web browser, type in localhost, hit enter, and nothing. You just stare at a frustrating connection refused error. You check your logs, the container is up and running, so why on earth does this happen? The crazy thing is, your container actually is running perfectly fine. But remember that container IP, 172.17.0.2? Because it's strictly private. Absolutely nothing outside your laptop can reach it directly. Furthermore, by default, your laptop is not forwarding any traffic to your container. Your Nginx server is sitting there diligently listening, but there is simply no door from the outside world into that private network. To solve this, you have to explicitly open the door yourself. We do this through port publishing. When you start the container, you use a publish flag, like -p 8080:80. By doing this, you're telling Docker to write another NAT rule. Now, when a web request hits your laptop on port 8080, your host machine intercepts it, rewrites the destination to the container's private IP on port 80, sends it across the bridge, and Nginx finally answers your request. But wait, there's a massive catch here that trips up even experienced users. The application inside the container must be configured to listen on all addresses, represented as 0.0.0.0. If your application, like Nginx, is bound only to localhost inside the container, meaning 127.0.0.1, that forwarded traffic coming from your laptop will hit a brick wall. You'll still get a connection refused error, even though you publish the port flawlessly. Let's wrap this up with Section 5, Rules of Docker Troubleshooting. And this brilliantly illustrates the whole system coming together. It really all comes down to two simple concepts, where your host machine acts as the ultimate middleman translator. For outbound traffic, NAT rewrites the source IP. The container quietly borrows your laptop's identity to talk to the internet. For inbound traffic, NAT rewrites the destination IP on the way in, but this only works for the specific ports that you have explicitly published. The host handles translation in both directions. Once that specific flow is clear in your mind, half of the Docker networking questions out there simply answer themselves. Let's do some rapid-fire troubleshooting. If your container can reach the internet, but you can't reach the container, well, you probably forgot to publish the port. If two containers on a bridge can talk, but a third one can't, that third one is definitely sitting on a different network. And if you're getting connection refused despite publishing your ports correctly, go check if your application inside the container is listening on 0.0.0.0 instead of just localhost. Knowing the theory and visualizing these concepts is a real game changer, but actually doing it yourself? That's what makes the knowledge permanent. Now that you've traced the exact path of your data and understand the translations happening under the hood, are you ready to put this into practice? Fire up the free CodeCloud hands-on lab linked in the source description. Run the commands, watch the containers start talking, and experience this networking magic firsthand. So, what kind of network will you build first?